Thank you for the introduction. Thanks to the organizers for the invitation and to participants for coming here. And also I would like to thank Serum for hosting this conference. It's always a pleasure to be here. It's one of my favorite places in the world. So I would like to tell some stories, and please forgive me, there will be almost no proofs. The goal is to show some ideas, and also I'm happy that approach of geometry, topology, and dynamics helps to solve some combinatorial problems, which might be sort of close to some objects which are common for this conference. So I suggest the following model problem. Let us study meanders. Meander is an object which is presented here in the picture, and which is just a smooth, simple closed curve in the plane transversely intersecting the horizontal line. According to the survey article of Landau and Zvonkin, the notion meander was suggested by Arnold, but apparently it appears already in the works of Poincaré, and it appears here and there in other branches of science, so in physics, in biology, quite a natural object. And the problem is, which is still an open problem, is to count meanders. So you impose the number of crossings of this blue simple closed curve with a red horizontal line, and the question is, what is the asymptotics for the number of meanders with at most n crossings? So there is a conjectural formula, which is conjectured about 20 years ago, but there is still no proof. So, of course, one can play with meanders in different ways. In particular, one can chop our meander along this red line, open it up, and we get pair of arc systems, chord diagrams, if you wish. We can also compactify the plane, wrapping it over a sphere, and then a meander is just a pair of simple closed curve transversely intersecting on a smooth sphere, and with a naturally, ordered pair. So we know which curve is red and which curve is blue, and the equivalence relation is sort of obvious. And also we can cut the sphere into two hemispheres, and we'll get two chord diagrams on each of hemispheres. I suggest the following particular setting for studying meanders. So if we cut the sphere into two hemispheres and we get this chord diagram, then we can consider the dual graph to this chord diagram, which is rather a tree. Well, in this particular case, since we're working with spheres and disks, it would be a tree. And I suggest, so you have to imagine that there are plenty of these blue arcs. So there are plenty of valence of vertices of valence 2, like this one, like that one, in this tree. Let us suppress them. They do not carry any combinatorial information. And what remains is a tree for each of the two hemispheres with vertices of valence 1, 3, 4, etc. And let us memorize this tree. This would be sort of a combinatorial passport of meander. And I suggest to count not all meanders at once, but fix this combinatorial passport and count meanders having this particular combinatorics. So, for example, in this particular case, let us count meanders with at most n intersections with this red line, having two trees of this Mercedes sign 4. It is much easier to count chord diagrams. So coming back to this picture, if I just consider a disk, a tree like this, and I put blue arcs and impose the number of these blue arcs, it is sort of an easy problem to count how many arcs you can construct. But then when you glue two hemispheres together, depending on the twist, sometimes you get from these blue arcs a simple closed curve, and sometimes you have a curve with several connected components. So here is the easiest example. So this is sort of a tennis ball, and here we have just one simple connected closed blue curve. And if you turn it by quarter of turn, you get two blue curves. So attaching arc systems on a pair of hemispheres along this common equator, we might get sometimes meander and sometimes not. Let us do the following. Let us fix a pair of trees, the tree on the northern hemisphere, the tree on the southern hemisphere, and let us construct all possible n-arc systems with given combinatorial passport imposed by the tree on northern hemisphere, with given combinatorial passport given by the tree on the southern hemisphere, and also all possible twists. And here the number of arcs is bounded by some very large bound, upper bound n. So we consider all possible pairs of arc systems, and let us count what part of these arc systems provide meanders. So in numerator we have number of triples which give rise to meanders, and in denominator we have all possible triples. So the question is, morally, I'm asking what is the probability to get a meander imposing this combinatorics on top and that combinatorics on the bottom. So the question is how this quantity behaves as the bound for the number of arcs tends to infinity. Does it decay like power function, like exponential function? In both cases, what are their corresponding exponents, and how do they depend on the trees? I should say that, at least for me, intuitively, the fact that this quantity should tend to zero was sort of obvious. Why, having 1 milliard arcs and gluing them randomly, can you get just one simple connected curve? And surprisingly, for any pair of trees, there exists a strictly positive limit as n tends to infinity. So the probability to get a meander, just a single connected curve, is not zero. It is computable. For example, in this very particular situation, which was constructed, well, which was treated in the first picture, the probability is approximately 1/3, or more precisely, it's this specific number. And so it's not even so small. And one can give an explicit answer for any pair of trees, and it is curious that it does not depend on, the answer does not depend on trees on themselves. The only information which is important is the total number for two trees of vertices of valence 3, or valence 4, or valence 5, etc. As soon as you have these numbers, you get the answer in terms of this number of vertices of different types. And also one can modify the setting slightly. So once again, I do not want to count all meanders simultaneously. I want to impose some extra combinatorial parameter and fix this parameter and count meanders with this given parameter. Before, as parameter, I used this as combinatorial passports to trees. Now let me loosen this constraint. Let me impose just the number of ends of the trees, the total number of vertices of valence 1, the number of leaves. So I denote the total number of leaves by p, and I consider all possible trees having in total, pairs of trees having in total p leaves together on top and on the bottom. And I consider all possible arc systems and all possible twists. I glue things together, and I compute again the probability to get a single connected curve. And the answer is given by this formula. And the thing is, red is not defined yet. It will appear in a second, but this is the geometry beyond. So what will appear in a second and what would allowed to count the meanders is the volume of the moduli space. So this is the, if you wish, the Masur-Veech volume of the moduli space of meromorphic quadratic differentials with at most simple poles. This is sort of the Masur-Veech volume of the cotangent bundle to MGN, to the moduli space of hyperbolic surfaces of genus G with n cusps, or complex curves of genus G with n punctures. And this is some related quantity. So there is geometry beyond, and this is the what I find curious in this story. So, and up to now I promised to count meanders, and instead of that I counted probability to get a meander. Let us count meanders now. And let us count meanders in this setting which was suggested on the previous slide. So as an extra combinatorial parameter, I fix the number of these minimal arcs. Sometimes they are called pimples. And to make things funnier, I want to separate meanders into two groups. Those which have maximal arc, which goes from the rightmost point to the leftmost point, and those which do not have an arc like this. So an arc like this sometimes is called rainbow. So I will 5 here denote the number of these minimal arcs which are colored in black. Plus says that we have a rainbow. And here minus says that we do not have a rainbow. And I impose, so I fix this number 5, and I let the number of crossings n, the bound for the number of crossings n, go to infinity, and I want to find asymptotics as n goes to infinity of number of meanders of these two types with number of crossings at most n capital. Once again, there is something, for the first glance, a little bit counterintuitive. Because here we have very special meander. We sort of impose an extra condition. So initially one may think that the number of meanders of this type should be smaller. On the contrary. So once again, so here's the asymptotics, and if you wish, you can look only at second lines. So it's power function in n, and for m plus, when we have this maximal arc, the power of n is 2p minus 4, where p is number of minimal arcs. And when we do not have maximal arc, it's 2p minus 5. So it's 1 less. So there are much more meanders which do have maximal arc than those which do not. And this is the sort of the goal of the story. This is the coefficient in terms in front of this n power 2p minus 4. And once again, this red thing was not defined yet. It would appear in several moments, and it is also, it's part of the volume of corresponding moduli space. So this was, consider this as sort of a motivation. And also, for simplicity, I spoke about meanders only on spheres. But you can imagine that you can consider analogs of meanders on any surface of any genus. And instead of considering only one red curve, you can consider multi-curve. So basically, all this stuff is counting pairs of smooth transverse multi-curves up to natural equivalence relation. In some cases, the answers are reasonable. In some cases, they are not so explicit. In some cases, they are very nice asymptotic formulas when genus tends to infinity. Now, let me, so it was sort of mystification. Let me demystify the story. To demystify the story, I have to first introduce, at least in several words, the moduli space I was speaking about. And I will introduce it in two different ways. One would be naive way, a space of translation surfaces, and the other way would be sort of more fancy, analytic way using analytic language. They are synonymous. So the simple-minded way is the following one. Let me first construct plenty of flat surfaces. So, and I will construct them in the following way. I will take a broken line composed from several vectors. So here there are 4, you can take 10 or 13 or whatever. And let us construct another broken line using the very same vectors starting from the very same point, but placing these vectors in different order. So I just choose a permutation and I place the same vectors according to this permutation. So since we use the very same vectors and we started from the same point, we'll arrive to the same point. And if we're at least a little bit lucky, the 2 broken lines wouldn't intersect. And being lucky is an open condition. You can deform any of these vectors and it would be still a polygon. And I don't want to bother you with details, but you can impose some conditions on permutation and some other stuff, and which would assure that you will have at least an open domain in the space of parameters which provide a polygon. It is sort of quite an easy exercise. So I think that you are at least convinced that you construct plenty of polygons of this type. And now I will construct a surface from this polygon, identifying corresponding vectors by a parallel translation. So by construction, the sides of our polygon are distributed into pairs, where in every pair, 2 sides are parallel and have equal length. So we can identify by parallel translation. And actually, you know this construction perfectly well. It's sufficient to take 2 vectors. And then we get a parallelogram. And we glue a torus from parallelogram as usual. So this is just a straightforward generalization of standard gluing of a flat torus from a parallelogram. And we get a perfectly flat surface of, in general, high genus. And similarly as for the torus case, our flat metric is perfectly smooth on the places which come from sides of the polygon. And no, there is no contradiction with the Gauss-Bonnet theorem, because now when we have a polygon which is more complicated than parallelogram, we'll have conical singularities. So in this particular case, for this particular permutation, one can immediately check that all the vertices of this polygon would be glued to one single point. And cone angle around this conical singularity, so you can view it, see it as follows. Say, let's start turning around this point. So I get to the beginning of vector v1, then I jump immediately here, I continue turning, I get to the end of v2, I jump here, I continue turning, and you will see that you will turn around everything. So you will turn around 6 pi instead of 2 pi. You have all the troubles with curvature. So this is genus 2 surface, but all the troubles with curvature are hidden in one single conical singularity. Otherwise, this surface mimics perfectly well flat torus. In particular, the holonomy of the metric is trivial, similarly as for the torus case. And it's obvious because as identifications we used only parallel translations. So if you take a vector and you make a parallel transport along a closed curve, it would necessarily come back exactly in the same direction. And it is convenient in this story, working with the corresponding moduli space of all these flat surfaces, to incorporate a choice of direct or vertical direction to the north, as part of the structure. In this sense, I consider a surface obtained from this polygon and of the polygon turned by some angle 23 degrees as 2 different flat surfaces, because the vertical direction is different. And I can apply this vertical direction at a single point of this, at some point of the surface, and transport it everywhere, and I would never get contradiction because metric has trivial holonomy. Note also that, and I will use it in very short time, that if I choose all these vectors integer, so suppose that all of them have integer coordinates, then our surface will be able to tile our surface with unit squares. It would appear in a second. Or if I will choose all these vectors to have rational coordinates, both rational coordinates, then I would be able to tile the surface with tiny squares of smaller size. And also it is clear that there is an entire deformation, well, that there is a family of flat surfaces like this. I can deform any vector, and it will deform my flat metric. Note that, yeah, this I already told, so note that I'm working not with space of polygons. I insist I work with a space of flat surfaces, of translation surfaces. So in particular, at any point, you can choose one polygonal pattern of your surface or another polygonal pattern of your surface. So you can, for example, for this, for the surface glued from this polygon, you can chop this polygon along this diagonal. And since this side is identified with that side, you can take this pentagon, put it here, and glue the two pentagons along these two sides, and you get this pattern. So this is implicitly, this shows why we get moduli space. We have very close, already in this picture you see a very close relative of mapping class group, right? Now I would like to suggest synonymous description of the corresponding moduli space, and you will recognize the moduli space which is probably more familiar to you. So note that our polygon, we can declare that our polygon, initial polygon, which was used to glue the flat surface, lives not in R2 but in complex plane. And then we have complex coordinate on the polygon. And when we're gluing the sides of the polygon, locally, in local charts, the identifications are local coordinate z prime is equal to local coordinate z plus constant. So our identifications, our gluing rules, are extremely holomorphic. And an exercise in complex analysis is to verify that the corresponding complex structure extends to points which come from vertices of the polygon. So formally you have first puncture them and then verify that your complex structure extends to this point. It does. It's an exercise. That's not all. Consider a holomorphic one-form dz in the complex plane. Coordinates are defined globally on the polygon but not defined globally on the surface. But the form dz is already defined globally on the surface obtained from identifying corresponding sides of the polygon. That's just because all our gluing rules are local coordinate z prime is equal to z plus constant. This is our parallel translation, right? So when you pass to differential, dz is equal to dz prime. So we get globally defined holomorphic one form on the surface, and once again, formally you have to first puncture the vertices and then verify that this holomorphic form extends to these points. It does. And these vertices, these conical singularities, are exactly the zeros of this holomorphic one form. So we see that these two structures are synonymous. This translation structure or the structure of complex structure on the Riemann surface plus holomorphic one form. So basically we're considering the following moduli space. You can consider the moduli space of curves or whatever you prefer, the moduli space of complex curves or moduli space of hyperbolic surfaces without boundary, without cusps. You can consider the vector bundle, which is the bundle of holomorphic one forms over this moduli space, and consider the total space of this vector bundle. Take out the zero section. I don't want to consider zero holomorphic one forms. So, and in this total space of g-dimensional vector bundle over the moduli space of curves, we have natural stratification. So holomorphic one form in total has 2g minus 2 zeros. But these 2g minus 2 zeros can be simple. We can get 2g minus 2 separate points on the surface. But similarly as for polynomial, 2 zeros can glue together and you had double zero, or 3 zeros can glue together and so on. So we get strata where we impose multiplicities of zeros. M1, so zeros, so this particular stratum is the stratum where we have exactly n zeros, with multiplicities m1, etc., mn, such that sum of these multiplicities is equal to 2g minus 2. And it is not so difficult to verify that the corresponding stratum is modeled locally on the vector space, which is the first cohomology of the surface, relative to n points. For every point of the stratum, we have exactly n zeros. So we have n distinguished points. So we have finite set containing n points. And we consider the first cohomology of this surface relative to this finite set with complex coefficients. In other words, we're considering not only absolute periods of our holomorphic one form, which are integrals over closed cycles, but also we add information about what is the integral of the holomorphic one form along a path joining any pair of zeros. As soon as you know all these absolute periods and n-1 relative periods, you have period coordinates in your moduli space. And actually, you can recognize these period coordinates. Do you agree that the sides of the polygon which appeared in the beginning, if you consider the sides not as vectors of R2, but as complex numbers, these complex numbers are exactly the integrals of the form dz over the corresponding segment. So the sides of our polygons are exactly these relative periods. Okay, now geometry starts. It's not an abstract vector space. It's cohomology. So we can consider cohomology with complex coefficients, or we can consider in these complex coefficients z plus iz. We have a natural God-given integer lattice in our vector space. So as soon as you have vector space endowed with an integer lattice, you have a distinguished volume form in your vector space. Because your lattice allows to normalize linear volume form. You declare that the volume of the fundamental domain of your unit lattice, of your lattice, is equal to 1. This is a fancy way to say that if you consider just naive Lebesgue measure associated to your vector coordinates which were used to define a polygon, it does not depend on polygonal pattern. If you choose one pattern or another, you will define the same measure in this corresponding space of translation surface. Well, this space is disastrously non-compact because you can scale the flat surface by any number, or the same multiply your one form by any number. So the way to compute volumes of spaces like this is, for example, to pass to a unit ball, this is one solution, or to pass to some hypersurface and to compute the induced hyper area of the hypersurface. This is basically equivalent things. So it's almost the same. So here we can consider the real codimension 1 subspace of translation surfaces having area 1, which is defined in these period coordinates by quadratic equation in absolute periods. We get sort of a unit hyperboloid in the ambient space. We have induced, so as soon as you have space with volume form and hypersurface, which is a level hypersurface of some function, you get induced volume form on the hypersurface, right? So I suggest to measure the hyper area of the corresponding hypersurface, and a non-trivial theorem of Masur and Veech, which is one of the basic facts in all this story, is that the total volume of any stratum like this, of Abelian, or there is a slight generalization of quadratic differentials, is finite. And for those who are familiar with, for example, space of measured geodesic laminations and with Thurston measure, this is basically the same thing, right? We have piecewise linear structure in the space, the corresponding induced volume form, and in the space of measured geodesic laminations we have Thurston measure. Here we have this Masur-Veech volume form. So now, first remark is that my option was, since we're working this piecewise linear space with natural Lebesgue measure, the volume of the entire space is infinite, but we can choose either unit hyperboloid and measure the induced volume, or what is almost the same, we can consider a cone or sort of a unit ball. This gray region is sort of a unit ball in our space, and we can consider volume of this unit ball. The hyper area of the corresponding surface and of the hyper area of the sphere and of the corresponding unit ball are related just by dimensional constant. So it's almost the same object. You can pass from one to another by multiplying by dimensional constant. Now, how can we count the volume of the corresponding unit ball? Well, we can take a small mesh, count the number of points in this mesh, and then make the size of the mesh tend to 0, normalize, and that's the volume, right? That's the definition of the volume. Now, since we can apply everything is homogeneous here, instead of considering a mesh with the size of the square of hypercube epsilon, we can rescale everything and consider a larger ball of large radius, and consider integer points inside this large ball, and then normalize. That's the same thing. So all this was an attempt to convince you that to compute the volume of the space, one has to compute the number of integer points which correspond to area of the surface at most n. Now, what are the integer points in our space? What are the points which are represented by integer points of this lattice? What does it mean that all absolute and relative periods of holomorphic one form live in Z plus IZ? Well, it means that our surface is a torus cover where all singularity points, all the branch points project to one and the same point. And the proof is quite simple-minded. Fix one of the zeros of this holomorphic one form. If all periods live here, then I can define a well-defined map which sends any point of the surface, now S is the surface, to the following complex number taken mod Z plus IZ. So I just join any point, any given point P with a fixed point P1 by some path. I integrate omega along this path, and I take this integral mod Z plus IZ. Now note that all relative periods and all absolute periods are here, so no matter what path I choose, the difference between two integrals would be in Z plus IZ. That means that when I mod over Z plus IZ, I get something well defined, and what is C mod Z plus IZ? This is t-dimensional torus. So we get, and it is an exercise to verify that this is a torus cover. What does it mean, torus cover? Standard torus cover. So basically it means that our surface is tiled with squares, like here. And you will say that these parallelograms are not squares. It is even better, because we have sort of polarization. We know what is the direction to the north. So we have to play, basically our problem of counting volumes is reduced to the following simplified version of Lego. You are given 1 zillion of pieces of squares, and you are asked how many animals, connected animals, you can construct from at least, using at least this amount of pieces of Lego, where all the pieces are the same, and there is vertical direction on one of them. And an extra condition is that you're allowed to have finite number of singularities, like here, of given types. This is the problem of counting the number of integer points in the corresponding stratum where we use at least n squares. So this is a problem which is similar to counting certain analogs of Hurwitz numbers. So here we have not Abelian differential, but quadratic differential. For quadratic differential, you have vertical direction, distinguished vertical direction, but without vertical line, but which is not directed. So for quadratic differentials, you're allowed to glue using flips, but preserving orientation. Well, it is the problem of counting these animals is not that easy. And the major progress was done by Eskin, Okunkov, and Eskin and Okunkov and Pandaripander, which made the following key observation. So when you are in combinatorics, I learned that when you are counting objects, you should, and you want to study some asymptotics, always do count objects with weight, which is inverse of the symmetry group. So for most of these square tile surfaces, there is this symmetry group is trivial. But for some of them, they might be more symmetric than others. And then you have to count them with weight, which is one of the automorphism group of the corresponding square tile surface. So mostly this weight is 1. And from time to time, it is less than 1. But it is extremely important to use this weight. For asymptotics, it does not matter, because they have very tiny amount of square tile surfaces where there would be difference in the weight. But for analytic properties of the corresponding generating function, it is crucial if you use this weight, and if you construct the corresponding generating function introducing formal parameter q power n, where n is number of squares, and now you sum from 1 to infinity, then so the authors of, well, Eskin, Okunkov, and Pandaripander proved that this function is a quasi-modular form, which allows really, and they obtain more information, which really allows to obtain volumes. In particular, it implies that all these volumes have the following arithmetic form. It's p power 2g, where g is the genus of the surface, times some rational number. So when I'm saying count, means find explicitly p and q, two integer numbers. So it is doable. It is not quite easy. You have to, it's rather an algorithm, but which can be programmed. And up to genus 10, it provides the volume for any stratum of Abelian differentials. For some stratum, like principal one, it provided answer up to genus 200. And very recently, Dawi Chen, Martin Müller, and Don Zaghir has constructed more general generating function, and which allows to compute explicitly volumes much further, and also which proved the conjectural asymptotic formula for genus which tends to infinity when all zeros are simple. So there much more information. Now there is still, for any concrete stratum, it is an algorithm. It's not just a compact formula, but there is one exception. As usual, genus 0 is much easier than other genera. In genus 0, one has just explicit formula for the volume, which was initially guessed by Kontsevich, and after quite a while was proved. And it is so simple that I cannot resist temptation to give you an answer. So define the following function of an integer number n, where n is, say, strictly positive, natural number n. So you consider product of all numbers n, n minus 2, n minus 4, etc. in numerator, and n plus 1, n minus 1, and minus 3 in denominator. You multiply it by the corresponding power of pi, and depending on the parity, you correct it by extra factor, which is either pi or 2. And you define by hands that minus 1 double factorial is and 0 double factorial is 1. So you can apply it also for n equal to minus 1 and 0. Minus 1 would represent simple poles, 0 represents marked points, and n would represent a 0 of degree n of quadratic differential. And then the volume of any stratum of meromorphic quadratic differentials with at most simple poles on a sphere is defined as 2 pi, and product of this function v along these degrees of 0. So it's very explicit, straightforward formula. The formula itself is of no importance. What is important for me is that it is very explicit and simple-minded. I will use it in a second. Now I need to give an idea how can one use all this stuff to count meanders. I have to give one more piece of information. So when we're counting square tile surfaces like this, note that any square tile surface like this can be decomposed into flat cylinders filled with closed horizontal curves. So let us consider maximal cylinders. So we have cylinder here, we have another cylinder here, we have some cylinders here. Well, there is finite number of cylinders, and the number of cylinders for given stratum can vary from 1 to g plus number of points minus 1. So there is some finite range of possible cylinders, and one can, why not? One can consider square tiled surfaces separately. One cylinder square tiled surfaces with at most n squares, two cylinder square tiled surfaces with at most n squares, and so on. So here's the answer for the stratum of holomorphic one forms with single zero of degree 3 and single zero of degree 1. So this is genus 3. So here P1, P2, P3, and P4 are relative contributions of one cylinder square tile surfaces, two cylinder square tile surfaces, and so on to the volume of the stratum. So each of them provides no zero contribution. So you can consider this as sort of probability to take a random square tile surface and to realize that it has one cylinder, two cylinders, three cylinders, or four cylinders. In particular, once again, everything goes in a complete contradiction with intuition coming from Morse theory. The maximal number of cylinders is not very probable. Now, once again, this slide is, these particular coefficients are of no importance, is just to convince you that the only answer which is sort of relatively compact and easily computable is contribution of one cylinder surfaces. It should not be so surprising, because combinatorics of a surface which is glued from one cylinder, so you have one flat cylinder, and then you impose some conditions on gluing, you subdivide circle on top and circle on the bottom into segments, and you identify the segments, and you want to get the surface of appropriate genus with appropriate singularities. So this, you can imagine that this combinatorics is somehow treatable. When you have to do similar things from 71 cylinder, it's already a nightmare. Even from 2 and 3 cylinders, it's already a nightmare. So the only quantity which is easy to compute is contribution of one cylinder surfaces. Okay, this I will use in a couple of minutes. And now I suggest, so I will need the following result. Take any region in our moduli space. For example, you can imagine it as follows. I constructed my initial flat surface from a given polygon. Let us deform a little bit. Let us consider an open space of flat surfaces, deforming a little bit each of the vectors. So we get small open neighborhood of the corresponding flat surface. And consider some rational grid. So consider only vectors which live in this rational grid, which have two rational coordinates which live in the corresponding rational grid. So we get rational grid in the open domain. Each flat surface like this, since it has rational periods, is tiled with tiny squares. So each point of this rational grid represents some square tiled surface, and we can check how many cylinders has this particular square tiled surface. And don't think that if you move a little bit, then the number of cylinders would be preserved. No, the cylinders are very narrow bands of these tiny squares which wind around the surface in some wide way, so this number of cylinders changes. So let us count what is the probability to get one cylinder surface or two cylinder surface and so on in this particular small tiny domain. Claim. It is the same as for the ambient stratum asymptotically when your grid tends to 0. So when you pass to grid which is more and more tiny, then asymptotically the probability, well, these proportions of one cylinder surfaces, two cylinder surfaces and so on, they do not depend on the place in your moduli space. They are everywhere the same. Wonderful. But this, one more theorem. And now, up to now, I was speaking about horizontal cylinders. But why not consider vertical cylinders? We can do the very same thing for vertical cylinders. And here is the second statement. So we can, so my notation is P is the sort of probability to get K cylinder surface, which is the contribution of all K cylinder surfaces to the volume. And I can count two quantities. I can count this Pk, so the contribution of all K cylinder, horizontally K cylinder surfaces to the volume of the ambient stratum, which gives this probability to get horizontally K cylinder surfaces. And I also can count sort of conditional probability. I can count the contribution of surfaces to the volume, of square tile surfaces to the volume, which have K horizontal cylinders and G vertical cylinders. And I can divide this quantity by the contribution of all vertically G cylinder surfaces. So basically what I'm computing is here, what is the probability to get a K cylinder, a horizontally K cylinder surface? And here it's a conditional probability. What is the probability to get a horizontally K cylinder surface knowing that it is vertically G cylinder surface? The claim is that conditional probability is the same as probability, that there is no correlation, that knowledge about the number of horizontal cylinder gives you strictly nothing about knowledge of distribution of vertical cylinders. So these two quantities are completely independent. Excellent. This would be used in a second for meanders, but now let me already use this fact, the fact that K cylinder surfaces are equidistributed to count approximately the volumes of moduli spaces, experimentally. Sorry, not explicitly, experimentally. So I take a convenient domain in my moduli space and I just compute statistics. How often do I see one cylinder square tile surfaces in this particularly convenient domain? This is one quantity, purely experimental. Separate quantity is I told that it is sort of relatively easy to compute rigorously the contribution of one cylinder square tile surfaces. Relatively easily, meaning that, for example, well, you have to use Frobenius formula, and if you want to go to use asymptotics, you use results of Zagier, which is morally his computation of the orbifoldic Euler characteristic of the moduli space. It's not completely trivial, but at least it is very doable. So we have the total contribution of all one cylinder surfaces to the volume, which we can compute rigorously, and we can compute the probability to get a one cylinder surface experimentally. So we just divide one quantity by the other and we get the volume. So this quantity we compute experimentally, so we get volume approximately, but at least it gives you a very good approximation and you can clean up all the possible factors of 2 which are missing and all the troubles with normalization constants which appear here and there all the time. It is basically impossible to compute anything correctly just by force of your spirit. So this, in particular, in this way, the algorithm for quadratic differentials, the algorithm elaborated by Eskin-Okunkov and Panderipande was implemented only recently by Elise Goujard, and it was very, very important to clean up and to check her formulas using this approach. Okay, now I can already tell how can one solve the meander problems. And first step is just to recognize that, as usual, that one object is the same as the other object. So recall that counting meanders is same as counting pairs of transverse curves on a sphere. Instead of considering only pair of transverse connected curves, let us consider pairs of transverse multicurves. And the first claim, so here is an example of a pair of transverse multicurves. We have a family of red curves which do not intersect between each other, family of blue curves which do not intersect between each other, and blue curves intersect with red curves transversely. My first claim is that this object is synonymous to square-tiled surface. And proof is very simple-minded. Just take the dual graph, consider this thing as a graph and consider the dual graph. It is easier to go in this direction. Let us consider square-tiled surface. For each square, I can take the point at the center and I can draw the horizontal red circle passing through the center. It would close up. And also I can draw a vertical blue curve passing through the center. So I will get collection of curves, and this particular square-tiled surface will give this particular collection of curves. So I'm claiming that, in other words, most of intersections here are just squares, but there are a certain amount of bigons which give this kind of vertices and several hexagons which give this kind of vertices, but, well, one can pass from one thing to another. So the first observation is, as soon as you have a pair of transverse multicurves on the surface, which is just a smooth surface, there was no other structure, you touch it and you get holomorphic structure on the surface, and either holomorphic quadratic, well, here meromorphic quadratic differential, or sometimes holomorphic one form, depending on topology of the multicurve. And counting this object as the same as counting this object. Okay, so what do we know about pairs of transverse multicurves on the sphere? We know how to count all such pairs, because this is counting volume of the corresponding moduli space, and we're lucky enough to have formula for the volume. That's why I showed the formula for the volume. It's simple-minded formula. Good. We can count multicurves where there is a single horizontal red curve and some complicated blue multicurve, because it's counting of one-cylinder surfaces in this language, and this is sort of easy. And we want to count meanders which correspond to one single curve horizontally, one single curve vertically, which is horizontally one-cylinder surfaces and vertically one-cylinder surfaces. But recall that we have a relation between these three quantities. So this we can count. This is all multicurves. This we can count. This is horizontally one-cylinder multicurves, pairs of transverse multicurves. And this is the object which we are interested in, but it was our relation of non-correlation, so I can come back to this previous slide. Oops, yeah, this is this relation. So this is all pairs of multicurves. This is, so I can put one here. It would be one-cylinder, horizontally one-cylinder multicurves, and here I can put 1, 1. It's vertical and horizontally one-cylinder multicurves, and here it's again 1. So I'm interested in this quantity, and I know the other ones. I can compute it, and I just took. So I can compute it by this formula, and in this way we count meanders. Okay, now let me finish, so I still have 6 minutes, let me finish with several further words about relation between Masur-Veech and Mirzakhani Weil-Peterson volumes of moduli spaces. So first, I apologize, I have to impose to you a whole bunch of objects which are ingredients of Mirzakhani's formula for the Weil-Peterson volume of moduli space of bordered hyperbolic surfaces with hyperbolic boundaries. So first I need to introduce very famous polynomials which depend on parameters g and n, where this is the genus of the surface, this is the number of boundary components. This, in Mirzakhani's formula, are length of hyperbolic boundary components, and this is a polynomial in B, and coefficients in this polynomial are expressed as intersection numbers of psi classes over the moduli space MGN bar. So here there is a combinatorial coefficient, and this integral is the following. So if you have moduli space, just forgive me for those who know it better than me, forgive me the reminder, but if you have a moduli space MGN of complex curves of genus G with n punctures, then having a Riemann surface of genus G with a distinguished point, say number 3, you can consider cotangent bundle, cotangent space to this point number 3. You get a complex line, and then when you vary surface on the point, your complex line varies. So you get family of complex lines which are parametrized by this space, and one can check that you get actually a holomorphic line bundle over MGN, and one can compute the first Chern class of the holomorphic line bundle. So we have n points, we have n very similar holomorphic line bundles, and we have n first Chern classes. So you can multiply them, rising to the appropriate powers, and if some of these powers sum up in the dimension of the space, you get the top degree cohomology class. You can integrate over this space, you get a number, and this is the corresponding intersection number. So this polynomial coincides with the top homogeneous part of Mirzakhani's volume polynomial for this Weil-Peterson volume of bordered Riemann surfaces, and if you want just borders of length 1, so which of length 0 cusps, you put these guys equal to 0. Now I have to introduce a formal operator which associates to a polynomial a number. Having monomial like this, I replace all the powers by factorials of the power, and I multiply by the zeta function of the corresponding power shifted by 1. So now I want to apply this thing formally to this all possible primitive simple closed curves on the surface of genus 2, or if you wish, you can consider B1 as a weight, and then we have all possible multi-curves in a sense. I consider multi-curves, I consider representatives in the orbit of the mapping class group. So having a multi-curve like this, I formally associate the following thing to it. So I cut the surface open along this curve, and I associate to this decomposition the following thing. So first, when I cut this open, I get surface of genus 1 with 2 boundary components of length B1, B1, and that's why I put here polynomial like this. I multiply by B1, just power 1, and here the red coefficient is responsible for the symmetry, and blue coefficient is responsible for the number of connected components which we obtain after decomposition. So for example, here we have 3 curves. When I open up, I get 2 pairs of pants, so I get twice surface of genus 0 with 3 boundary components of length b1, b2, b3. So since I have 2 components, there are 2 polynomials like this. I multiply by all these b1, b2, b3, and now there are these coefficients which are responsible of symmetries and numbers of components. That's the explicit values of these polynomials. They are really explicit. All this is computable. These intersection numbers are known, at least for all small pairs g and n. And then I apply operator which associate to a polynomial number, and I sum up, claim, I get the Masur-Veech volume of the moduli space Q2. So there is a relation, this is an example of relation between Masur-Veech volume and sort of Weil-Peterson volume, except that Mirzakhani uses from her volume polynomial the smallest degree part, and we need the top degree part. So the formal theorem is the following. To every decomposition like this, I associate a graph, which is once again a dual graph. Also, I can have cusps there indicated by these legs. And here's the formula for the Masur-Veech volume in terms of these volume polynomials. And this remark that finally for Weil-Peterson volume you need the constant term, and for Masur-Veech volumes you need the top homogeneous part term of the corresponding polynomial. And also one more remark is that up to some combinatorial constant, when there are no cusps, this formula can be extracted. It was obtained already by Mirzakhani, and we didn't realize it immediately. We proved it differently. And to finish, so this is the picture of Maria Mirzakhani, and this was, sorry, I would need just one more minute. One of the goals of this talk was to try to convince you that there are plenty of beautiful ideas hidden in her papers, and actually every single thing which I was telling today was supposed to be done by Mariam. The person from whom I heard about meanders during the last 20 years, I heard about them from 4 persons, and 2 of them in the last 2 years were Mirzakhani and Kontsevich. And I think that she was already thinking about counting meanders. And this equidistribution theorem was strongly influenced by the work of Mirzakhani on counting simple closed geodesics, and so on and so forth. And I want to finish with the following thing. So with the result with comparison of counting flat simple closed geodesics with hyperbolic simple closed geodesics. So we can associate, so this is my square tiled surface which appeared many times. And I want to encode its cylinder decomposition in the following way. So here I have one cylinder. I associate this edge to this cylinder. Here I have one more horizontal cylinder. This is this edge. These points with the cone angle pi correspond to simple poles of quadratic differentials, which are in this language correspond to cusps of hyperbolic surface, so they are half edges, and so on. So here is one more cylinder, so I have to put genera of the corresponding, so the points here for me, for this surface, are singular layers. I have to indicate what is the genus of the corresponding ribbon graph around singular layer, and what are the heights of the cylinders. Now, I can encode this thing also by a multi-curve. So here I have, this is the waist curve of the cylinder, but since it has height 2, I take 2 gamma 1. Here there is a cylinder of height 1, I have gamma 2. Here I have gamma 3, 2 gamma 4, and I have poles as indicated, and I consider a hyperbolic surface like this and a multi-curve on this hyperbolic surface which is drawn here. So recall one of the fantastic results of the thesis of Mirzakhani. Consider, for example, like here, 6 spheres with 6 cusps. You can have simple closed geodesics of 2 types on a sphere with 6 cusps. It can separate our cusps into groups 3 plus 3 cusps or 4 plus 2 cusps. You cannot separate a single cusp or not separate a cusp at all. And the result of Mirzakhani is no matter what is the hyperbolic metric, your sphere can have bottleneck, can be extremely wide, but no matter what is a particular hyperbolic metric on this 6-function sphere, the asymptotic proportion of simple closed geodesics of this type over simple closed geodesics of this type is 4/3 for any hyperbolic surface X in this family. Theorem, the very last one. So if you consider, well, and of course she has analogous theorem for multicurves. Here multicurve is particularly simple, it's just simple closed curve. You can consider multicurves and consider asymptotic proportion for multicurves. Claim, if you provide an interpretation of a multicurve as at the previous slide, then asymptotic proportion of simple closed flat multicurves is exactly the same as asymptotic proportion of simple closed hyperbolic geodesics. It's the same numbers as in Mirzakhani's result. Thank you very much for your attention. Думаю, arigato gozaimasu.